All right, my friends, chapter 9 is going to have quite a bit of review from pre-calculus. That's actually one of the things that I like about this textbook, is that it goes over kind of some important things right before it applies calculus to it. So section 9.1 is called conic sections, and last year in pre-cal we spent quite a bit of time on conic sections. This presentation will be a brief review over kind of the most important pieces. I can also include videos from pre-calculus if you are interested in more details. But really, this is just going to be a brief review of what conic sections are and how to analyze and graph them using their properties. So the warm-up says graph each relation. Let's have you graph y equals x squared, y equals negative x squared, x equals y squared, and x equals negative y squared. All right, perfect time to pause the video and make sure that this is something that you can do without having me do it. Part of the reason I have you pause the video and do problems on your own is because there's always more than one way to do something. And if you think it through in your own way first, and then I show you my way, it's a lot more likely that you'll understand my way, even if it's different than the way you thought it through. So trusting that you've done that. Okay, so since any real number squared is positive, I hope it makes sense that I drew this graph so that it only has positive y values, since y is just an x value squared. Vertex would be at 0, 0. Put 1 or negative 1 in for x, you'll get positive 1 out for y. Put 2 or negative 2 in for x, and you'll get positive 4 out for y. Make your dog globbier if you need to. Okay. For this one, y equals the opposite of x squared. Since x squared has to be positive, its opposite would have to be negative, which is why I drew an xy plane that would just have negative y values. So put plus or minus 1 in, you'll get negative 1 out this time. Put plus or minus 2 in, you'll get negative 4 out. There we go. Okay, for this one, instead of having a function of x like you had here, you have a function of y. So for this one, it would make sense to plug in y values and get your x values out. This is still your x-axis, and this is still your y-axis. So if you were to plug 0 in for y, you'd get 0 out for x, so there's your the origin. If you were to put plus or minus 1 in for y, you'd get positive 1 out for x. And if you were to put positive or negative 2 in for y, you'd get positive 4 out for x. So here we have a parabola that instead of opening upward or downward, could open horizontally. If you have a positive coefficient, it would make your parabola open to the right. And then here, if you have a negative coefficient on your squared term, it would make your parabola open to the left. So because this time your x coordinates, instead of being always positive, multiplying that positive value by negative would make it always be negative. Okay, so put plus or minus 1 in for y, you get negative 1 out for x. Plus or minus 2 in for y, you'll get negative 4 out for x. There we have it. Oops. Okay, so these would be for parabolas. These would be kind of your parent functions, or you could say parent relations, up to you. So vocabulary, some people would look at these last two and say these are not functions, and they're not functions of x, but they are functions of y. And the first two are functions of x, but they're not functions of y. So all of these, in a way, are functions. Yeah, okay. All right, example 1. Directions are graph each relation. And part A, let's have you graph y equals 1/2 times the quantity x minus 3 squared minus 5. And go ahead and graph that on your own, pause the video, and see how that goes. Now, I want you to be able to think about how to do this in a couple different ways. Back in, I don't know, maybe Algebra 1 would be maybe the first time you'd see something like this, Algebra 2 for sure. You would think of this as a y equals x squared graph, so something like this. You would notice that it got shifted to the left 3 units, and then down 5, and it has a stretch factor of 1/2. The only difference between the way this is written and the way that I'll probably start thinking about it from now on is instead of looking at the minus 5 right as it is, you're going to see me add it to the other side. So and it does not change the way the graph looks at all. I hope that is comforting. But what we can do, and this pays off for all the conic sections, is you can look at, this is still a y equals x squared parent function. It still has a vertical stretch of 1/2. It is still shifted to the left 3 units, and it's still shifted down 5 units. But the way that we think of that, I'm just going to kind of show off that this is inside of a function here. The way we can think of that is if you have addition or subtraction inside inside a parent function like this, if it's inside the function, like here, adding 5 is inside basically y to the first power, and subtracting 3 is inside x to the second power. So if it's inside the function, then it would kind of do the opposite of what you'd normally think. So some people think, oh, subtract 3, that would move it to the left, but we've learned that this would move your graph to the right 3. And then adding 5 with y, a lot of people would think that means go up 5, but if it's inside the function, it's actually always going to be counterintuitive. So you'd go down 5. So just a slightly different way to think of the same thing. So when you graph it, you want to be able to do 5 points of accuracy. Sorry for the weird scale here. So the vertex, of course, so to the right 3, down 5. And then from there, we're going to do our points of accuracy based on 2 things. What a normal y equals x squared graph looks like, and then your stretch factor of 1/2. So we're going to go to the right 1 unit and then up just 1/2. To the left 1 unit, up 1/2. To the right 2, normally you'd go up 2 squared, which is 4, but we're going to go half that distance, which is up 2. And then same thing over here, to the left 2, and then up 1, 2. And then we could fill it in. There we go. Something that doesn't look like a total train wreck right there. Okay. There we go. Okay, that's going to bother me forever, but I'm just going to let it be. Okay. All right. Part B. Let's have you graph. Negative 2x equals 4 times the quantity y minus 2 squared minus 10. Again, a super good time to pause the video. Okay, now let's think about this one. Notice this completed square here. I would caution you against expanding that out. We kind of like the fact that that is the way it is. I personally would add the 10 over. I like it when my shifting is inside a function. So I'm going to demonstrate adding the 10 over. And then I'm going to factor out the -2 because remember shifting rules only work if your coefficient on your variable is 1. So I'm going to factor out the -2. And then a note, we like our stretch factors to be on the squared side. So between having it on your first degree side and your squared side, let's choose to divide that -2 over so you can have your stretch factor on the squared side. So sort of like a vertex form for this guy would be something like this. So what is your parent function or parent relation? You could think of it as x equals y squared. I really like including my stretch factors in my parent function. It's totally up to you. But what I do is I think about what this graph would look like, and then I just shift that graph to the right 5 and down 2. Okay, so vertex it would have been at the origin, but got shifted to the right 5 down 2. And then this would be opening to the left. And then when you square your y movement, you're going to also multiply it by -2. So from here, we're going to go up 1. And then normally you'd go, y squared would be 1, but we're going to multiply it by -2. Same thing, 2, boop, boop. And then from here, I would go up 2. I'm thinking what's 2 squared? It's 4, and then I have to multiply that by -2. So I'd actually need to go so let's see, up 2, and then to the left 8, and then down 2 from the vertex to the left 8. There we go. All right, my friends, I hope this is making sense. So part C, let's do x equaling 2 times y squared plus 16y plus 33. Again, super good time to pause and see how you would do. So for this, since this is not in kind of a vertex form, we're going to need to complete the square to do so. So you're going to see, from me, you could leave the 33 here. You could kick it over to the other side. I think I'll go ahead maybe and just kick it over to the other side. For the y terms, I'm going to factor the leading coefficient out. And I'm going to leave a nice little gap there because I'll need to complete this square. So, so what's the magic ingredient for a perfect square here? So I'm going to take your linear coefficient, which is 8. I'm going to divide it by 2. We'll get 4. We're going to square the result, and we're going to get 16. Now, it's not okay to just toss a bunch of value on one side and think you still have a balanced equation. So what did I really just add? I really just added 2 times 16, which is 32. So there are 2 ways to balance that. You could subtract 32 off on the same side of the equation, or you could add 32 to the other side. And that's what I'm going to choose to do. So now what do I have? I have x minus 1 on the left side, and I have 2 times the quantity y plus 4 on the right side, or y plus 4 squared on the right side. And then I'm just going to exaggerate that is kind of inside a function. So let's see, what's my parent function this time? It's x equals y squared, or you could say x equals 2y squared if you want. And then you could see it got shifted to the right 1 and down 4. Okay, so let's see, x equals 2y squared, we said to the right 1 and down 4. So up and down 1, and then to the right 2. Up 2, to the right 8, because 2 squared is 4, but you're multiplying it by 2. And then down 2, and then to the right 8. There you go. And you've got 5 points of accuracy, vertex in the right place, all that fun stuff. Okay, if completing this square is an issue for anybody, just send me a message or an email, and I will be happy to make a video where I kind of drill and kill the process known as completing this square. If I don't hear from you, then I'll keep trying to kind of make sense of it as we go, okay? So in pre-calculus, I would have done all the derivations of the equations of the conic sections, but this year we kind of decide been there, done that, and so we just give the basic review, okay? So we're going to move on to not just graphing parabolas, but being able to find the equations of a directrix and its focus. So, so just a quick review. So 2 kind of important facts. So fact number 1, the value P, or I'll say the absolute value of what we will call P, that is the distance between the directrix and the vertex. And the word directrix could be taken out and replaced with the word focus in the vertex. Okay. Fact number 2 is that to find the value of P, set the stretch factor which, just to make sure you're clear on what I mean by stretch factor is the coefficient that you had on the squared side each time. So I think I'm going to add that in as fact number 3 because it's pretty important. And if you're doing it this way, you set the stretch factor equal to 1 over 4p. Now this is different than the way the textbook teaches it, and if you took accelerator pre-cal from someone other than me or pre-cal from somebody else, you probably would have done this a little differently, but I feel like this works better with the training that we've got, so this is kind of how we go about it. It's equivalent to whatever you may have learned in another class, I'm sure. And then fact number 3 is about the stretch factor. Whenever I do these problems, I will always treat the stretch factor is the coefficient of the squared term. Or I should say not the squared term really, but kind of like the squared side, like after you have completed the square. Like so, okay? So just some important facts as we go on. Okay, and when I write this, if you're like, oh, what is that hocus pocus? And this does not feel true based on your experience, then I really do encourage you to watch the pre-cal videos that I will include for this lesson. It'll be optional though, as to whether you want to do that, okay? Example 2. The directions are for you to find the coordinates of the focus and the equation of the directrix for, let's see, let's do it for example 1, parts A and B. So we'll have A, B work for redoing part A, and B work for redoing part B. Okay, so for these, I always think graphically. You can get really lost in an equation nightmare if you're not careful. So I always think about the graph. So recall, and if this does not sound familiar, do watch those pre-cal videos. But the a parabola was a set of all points that were equidistant from a directrix, a line, a fixed line, which was called the directrix, and a fixed point, which was called the focus. Okay, so for part A, you'd be looking for a horizontal directrix and then a focus that would be along this axis of symmetry of your parabola. Okay, so what were the coordinates? So you're going to start with a couple important pieces of information. So one, what were the coordinates of the vertex? So they were 3, -5. Okay. Next, I'm going to refer to fact number 2. To find the value of p, set the stretch factor, which is the coefficient of the squared side, equal to 1/4p. So your stretch factor here was 1/2. So if you set that equal to 1/4p and solve for p, you'll have that p value. So you could just eyeball it though. 4 times 1/2 would be that 2 right there. Or of course you could use cross products as well. But here your p value would be 1/2. Next, what does p mean? Well, the absolute value of p, which here the absolute value of p is just 1/2, is the distance between either the directrix in the vertex or the focus in the vertex. So, so what that means is that I put this dot too far away. It's really just half a unit away, and then the directrix would be half a unit away on the other side. Okay, so since your vertex was at 3, -5, your focus would be at 3, -4.5, and then your directrix would be at y equals -5.5. There we go. So I'll just make that official down here. Your focus would be at 3, -4.5, and then your directrix would be at y equals -5.5. Whoops. There we go. Okay, part B. Part B is same stuff, just for part B from example 1. So this time we're expecting a vertical directrix, and then we're expecting a focus somewhere along the axis of symmetry. So starting with the coordinates of the vertex was at 5, -2. Now to find the p-value, we'll set the stretch factor, which notice is your coefficient on the squared side, equal to 1/4p. Okay. Feel free to eyeball it or use algebra to solve cross products, clearing fractions, whatever works for you. So if I was to multiply both sides by say 4p, I'd have -8p equals 1, and then p is equal to -1/8. So the fact that your p-value is negative here just tells you something you already knew. It tells you your parabola opens to the left. But remember, the absolute value p is the distance between your vertex and the focus, which means I definitely have these two close to each other, but I'm just going to leave it. It's a concept picture. So, so the coordinates of the focus would be, so instead of at an x value of 5, you would have gone to the left 1/8 of that, or 1/8 of a unit. So you'd have 4 7/8. The y coordinate would be the same because you're just moving straight in to the left. And then this vertical line would have an equation of x equals, so this is at 5 again, and then you would have gone to the right 1/8, so 5 1/8. So to be clear, your focus would be at 4 7/8, -2, and then your directrix would be at x equals 5 1/8. There we go. All right, my friends, I hope that makes sense. In the next part, we'll take on ellipses, but this was just a quick review of parabolas. Take care, everybody.